I would like to start from your first page where let's go through a few formula here that I need to talk about. There's something important with each of the formula. For your binomial expansion, you're going to see that there is this a plus b power n in your formula list. You use this formula only when n is a positive integer. Okay, this is the one from your secondary school, your binomial expansion formula. Only if it's positive integer, you go for this. And I should let you know that when we look at each term, sometimes you're confused with the expansion. I don't really need to refer to the formula list. Each term is treated as always you have a choosing term. So n choose 0. We start with a power n, b power 0. Then we will just keep increasing the zeros to 1. Next term would be n choose 1. Then a, your power drops by 1. The other power increases by 1. So you keep in mind that we should always have 3 terms in each of the expansion here in the binomial expansion. It's sometimes used in other chapters as well, not just in this chapter, like complex numbers, sometimes they want you to expand. Okay, next, for your Maclaurin series expansion, we will always have this fx to be written in this structure. Just recall again what is f0. F0 refers to when x is 0, can we find the y value? And f prime 0 means you want to find the dy dx value from there. Okay, and so on. How many times you should differentiate your equation will depend on how much they want you to expand. If they want you to expand to x cubed, then you will have to differentiate 3 times, and so on. Second formula here, what is the difference between this power n versus the original power n at the top part? Okay, so the difference between them is if you're using this 1 plus x power n, your n is either a fraction or you can have a negative number. Okay, for these 2 cases, we will apply this particular formula. And when we apply this, you need to note that this must be a 1. So if it's not a 1, we will factorize out certain numbers to ensure that the left-hand side constant is a 1. There are 2 shortcuts that I want you to know. Let's note down below. My shortcuts are in relation to power minus 1. Let's say for this particular formula, you have got a negative 1 in the power. What are the shortcuts to apply? And these are usually commonly applied in exams. So if I have a 1 plus x power minus 1, your power of minus 1 will make the coefficients alternate in signs. And all coefficients will be 1, just that the signs alternate. You don't need to use that formula. If it's a power minus 1, directly go for this. It will be faster for you. Second, I can also have negative inside. But if it's negative, it just means that we're going to replace all the x to minus x. So that will become 1 plus x squared plus x cubed, and so on. It's even easier. The first one is all with alternating signs. The second one, everything plus. You don't need to show the proof. You can use these shortcuts directly in the questions. Okay. Otherwise, for the rest of the expansions, you just need to be able to recall what is available to you. Formula list, think of it as it comes in pairs. Ex and ln, both available. Sine and cosine, both available. Your right-hand side on the formula list is giving you a valid range. You usually ignore this unless the question asks for a range of x that is valid. Okay, so only the first and the last has special conditions. The first one, you always want mod x to be less than 1. For the ln, you just take note that it's not inclusive at negative 1. And the reason is because when it's minus 1, you sub into your ln equation, you will get ln 0. And we don't want to have ln 0. That's why they don't include minus 1. Okay, let's do the questions together. We go to the next page, then I explain more from there. We start with a foundational problem first. Let's say you have got this equation given to you, And we know that we must differentiate to get the dy dx to show. But never start the problem blindly. Step 1 should be to try to consider to manipulate the equation. Don't start thinking of whether you should differentiate straight away. Your first thing should be go and adjust if necessary. For example here, I may want to move the tangent across. You will consider that. I may want to have this to appear first. I move tangent across to the right side to get tangent inverse. So which is better? Can we differentiate from the original or from this? For this question, both should work out fine. However, if I differentiate tangent, I get secant squared. Since I don't see a secant appearing, I may not want to have this. Okay, I go straight with the second formula. We differentiate from this instead. Okay, so there's no hard and fast rule to tell you which, but in this instance, this is a better approach. So let's differentiate this equation with respect to x. Left-hand side, I get half dy dx. Tangent inverse formula, we go for 1 over 1 plus this square. Continue to differentiate within the bracket, I get a root 2. So to get it to the show, I just need to cross multiply my equations. Okay, that's your part 1. Part 2, we follow up with that part 1 equation and they tell me, can you find for me the first 2 non-zero terms in the expansion for y? Now, although they say expansion for y, it is not necessary to make y the subject. All your differentiations are still valid for your equation. In order to get the 2 non-zero terms, I have to start substituting. They never tell me to what powers. So I have to start substituting to observe whether the values are 0 or not. So what's the first value? If I substitute x to be 0, I get half y is tangent inverse 0. In Maclaurin series, you always put x as 0. So my y value will be 0. I need the next one. We go to the dy dx equation. Again, you put x as 0, we check the dy dx. This dy dx happens to be just 2 root 2. But we only have one non-zero term now. I'm supposed to get 2 non-zero terms. So we don't have a choice. You have to differentiate again. Okay, let's do the next round of differentiation. Just be careful, there will be a product of 2 terms over here. You have to go for product rule. So to do product rule, let's keep the 1 plus 2x squared. I differentiate dy dx, we get d2y dx squared. Keep dy dx. Differentiate 1 plus 2x squared, we get 4x. And right side, 0. Let's sub again to check whether you get a non-zero term. You sub x to be 0. Unfortunately, the other term here has x as well. So your d2y dx squared, when you substitute, will still be a 0 term. So we have to do one more round. Now, both terms are a product of 2 terms. Just be careful when you work through the product rule. We have to carefully differentiate. I keep the 1 plus 2x squared. Differentiate this, we get the 3y dx cubed. Keep the 2y dx squared. Differentiate this term, we will get 4x. Second pair of product, keep dy dx. Differentiate 4x is 4. Keep 4x, differentiate dy dx. Let's substitute one more time. But there are terms that immediately become 0. These two underlying terms are 0 because the x is 0. So we just have another two terms left to check. Your d3y dx cubed plus dy dx, make use of the value previously, it's 2 root 2. So plus 2 root 2 times 4 is 0. And I can find my d3y dx cubed. We take all these numbers that we have found so that you can apply the Maclaurin series formula. F0 plus dy dx times x, 0 x squared, and then minus 8 root 2 over 3 factorial x cubed. Simplify the equation. Okay, that's your part 2. This is the Maclaurin series. So next part, they want to use standard series from your formula list to find out what is this expansion. Your standard series will be applicable for the denominator. Denominator has a cosine 2x. And we should see that this term from the numerator is actually from the initial equation. 2 tangent inverse is your y. If you move the 2 across, you really will get 2 tangent inverse of this term. So this top part we should use from part 2. It's the same expansion, same y. Denominator we take from formula list. Formula list, we take the expansion. I'm only looking at up to x cubed. Okay, so let me apply those two numbers accordingly. Okay, I work on part 3 below here. I'm looking at 2 tangent inverse root 2x divide by cosine 2x. Numerator, let's use part 2. Denominator should be taken with reference from the formula list. Okay, so I just write out what we should get. We will get 1 minus, since ours is 2x, we will have 2x squared over 2. It's from that first page formula list formula for cosine. Any of such questions with fractions, to further simplify, move the denominator up. You want to write as power minus 1. Okay, denominator move up is power minus 1. Negative powers, we are going to use this expansion. Okay, I just rewrite for you to recall. I need only 2 terms, so I just write the first 2. The formula says we are going to have 1 plus n times x. Your x in this situation should be this term. This is your new x, excluding the 1. Minus 2x squared is the new x that you will put into the equation. Okay, let's expand out. Our 1 plus nx will give me 1 plus 2x squared. Okay, nx, so minus 1 times this is positive. You only need to write in the terms that will be degree 3 and smaller. So I will be expanding this and this. Those that are larger than degree 3 don't need to write. Okay, so let's do the expansion. Sometimes you may see in solutions or from my solutions that I use an approximate sign. You write in an approximate sign if you want to drop the dots at the back. So we are trying to say the two lines are approximately equal, but I didn't write in more terms. Okay, so sometimes when you see approximately means at that line, I have dropped the dots. So we say the two lines are approximately equal. Okay, let's go on, next part. It's still on the same problem, but I want to talk about a few explanation questions. They say that, can you use the series that you have found? Let's find an approximate value for this. This was the original y that we have. I've printed the answer there. It's just with graphing calculator. We change this term into the expansion. Once I change to the expansion, to get these numbers, this is from the graphing calculator. Remember, GC can do integration. But what is important is, how do you explain? Is it a good approximation for us or not? When I change this to the series, is this considered good? What should we be considering? Let me write in the logic first, then we fill in the answer. The logic is, in the expansion here, we had neglected certain terms. I had neglected x power 4, x power 5, and so on. We stopped at degree 3 based on the question's requirement. If you had neglected them, okay, you need these terms to be small. You need x power 4, 5 to be small so that the values are negligible. You are dropping terms because we think that they will be negligible values. So what is considered small? So I want x to be close to 0. The closer it is to 0 will mean that that value, when you raise to power 4 or 5 onwards, it will be very small numbers. Okay, so you want x to be small, close to 0. Let's check on our integration. My integration is from 0 to 1. Those near zeros are fine, but 1 is not small. Small values are really those 0 point something. Anything close to 1, you sub in 1 power 4, it is significant enough. 1 power 4 is 1. Okay, so to explain, we want to say the following. We let them know that the series refers to the expansion. Okay, my series will differ significantly. Okay, use this phrase, differs significantly, okay, at x values close to 1. We are letting them know that our integration have an issue close to 1. Okay, then you can say, hence, approximation is no good. As a follow-up question from this, they may ask you to calculate the original integration. Okay, let me call this as the original equation. Again, the calculation is from graphing calculator. I have given you the value. And what is important then is they will ask you to compare those two. Can we calculate what is the percentage error in the previous part? Give me a way to reduce this percentage error. How do we calculate a percentage error? Percentage error should be thought of as the difference between the two numbers divided by the original value. Okay. Percent error. Error, you divide by the original and you multiply 100%. This will give you percent error. I will then take the two numbers. This is the initial expanded value from the Maclaurin series. This is the original. Can we take the difference between these two and divide by original? So your error here in this question will be, we take the 1.1338, subtract 0.943, divide original, and we multiply 100%. Okay, so the value, if we calculate, we will get 16.8%. So this is the percentage error. How do we reduce? You want to reduce this percentage error, how do we explain? I've talked about it here. The logic is we neglected too many terms. So the more terms you use, the better it will be. Okay, so you explain it this way. To reduce the error, we could use more terms in the expansion. Can quote certain terms, you can say such as degree 4, degree 5, and so on.